So as we pick up where we left off talking about multiplication rules and independence, one of the things I wanted to kind of review with you first was just the concept of independence. So just a couple examples here of two events and determining whether they're independent or not. So number one, you have event A is flipping a coin and getting heads, and event B is rolling a 4 on a fair die. And the question is, are these events independent? So remember, when we're talking about independence, we're talking about, does the probability of one of these two things happening have an impact on the other? So since when you flip a coin, that has no impact on the probability when you roll a die, we would say that these two events are in fact independent. For number two, we have choosing a heart from a deck of cards as event A, and event B is choosing a 5 from a deck of cards. And note here that this is being done with replacement. So since this is being done with replacement, both events would be chosen out of 52 cards. That would also make both of these events also independent. Whereas with number 3, if we went to do the same thing, but we did it without replacement, what would occur with event A is you would be choosing event A out of 52 cards, but since you didn't replace the first card before you draw the second, you would be choosing only 51 cards out of event B, and because of that, these events would be not independent. And then number 4, 2 students in our class are chosen for an all expenses paid trip to 10th period. Event A is student has blonde hair. Event B is student is a girl. So once again, assuming we're talking about the number of students that are in our class, we would have, for event A, 27 students to choose from for event A. And then when we went to choose the second student, we wouldn't want to choose the same student twice. So event B would be out of 26 students. So these two events here would also be not independent. So 3 and 4, the reason that both of those events are not independent is because we're not replacing either the first card or the first student in case of number 4 before we draw the second. So some different things we're going to look at in regards to probability has to do with tree diagrams. So just a simple example here, and we have consider flipping a coin twice. And the question says, what is the probability of getting 2 heads? So one of the ways that we take something like this and try to organize our thoughts with this is to make what's called a tree diagram. So a tree diagram starts with what you're doing. So in this case, we're tossing a coin. So on the first toss of the coin, I can get heads or tails. And just note that I put the probability of when I flip a coin of what getting heads or tails is there. And then if you go to this part here, if you flip the coin and get heads, when you go to flip it a second time, the possibilities are heads and tails. Notice, once again, probabilities for each of those events are 1/2. If when I flip the coin the first time, I get tails on the first try, then when I go to flip it again, once again, I could get heads or tails. And note the probabilities that go with each of those there. So what a tree diagram kind of represents here, let me kind of clean this up. So this right here represents getting heads and then heads again, which is this right here. Then this right here would be representing getting heads and then tails, which is what this is here. And then this part of the diagram here would be getting tails and then heads, which is what this is here. And then finally, this part of the diagram here would be getting tails twice, which is this here. So if we're talking, what's the probability of getting 2 heads? Well, if you notice here, there's only one of those outcomes that occur out of 4 possible outcomes that you could have for something like that. So that's why the probability for something like that would be 1/4. Another way of looking at this would be to say from the tree diagram, if we take our probabilities here, getting heads on the first draw is 1/2, getting heads on the second draw is 1/2, and because those two events are independent, what we can simply do is just multiply their probabilities together. And that's another way of answering a question that is like that there. So different example with a two-way table, and the question here says, suppose we choose 2 students at random. Draw a tree diagram that shows the sample space for this chance process. So I'm going to start first with handedness, left-handed, right-handed. So here's my starting point, and what I have here is, first, I could choose a student that's left-handed, or I could choose a student that's right-handed. So I have that there. And then, if I choose a student who's left-handed, that student could be a female, or that student could be a male. Same with someone who's right-handed. If I choose a student who's right-handed, the same thing occurs. I could choose a right-handed student that's a female, or I could choose a right-handed student that's a male. So that would be a tree diagram that shows the sample spaces. So in terms of listing what they are, one of the parts of the sample space could be is I could choose someone who's left-handed and is a female. So I could put that like over here. And that's what this part represents there. I could also choose someone who's left-handed and is a male. So I could have something like this here. Then I could choose someone who's right-handed and a female. So I'd have that there. And then I could choose someone who's right-handed and is a male. And I'd have that there. So some different questions that come up with two-way tables and probability. And a question here says, find the probability that both students are left-handed. So in terms of finding the probability that both students are left-handed, that could be a student who's a female and is left-handed, or a student who is male and is right-handed. So if we're talking about using the multiplication rule for this, so what we're basically looking at here is we're trying to choose the first student is a lefty, and I'm kind of coming down to the bottom here for this, and I'm going to show you a formula for this in a moment. But if we're talking about choosing two students that are left-handed, we're basically trying to find what's the probability that the first student is left-handed and the second student is left-handed. So the probability that the first student is left-handed, and if you notice here we have 4 left-handed students, and this is out of 28 total students. So that's where the 4 out of 28 comes from here. So if we're choosing two students at random, so obviously we would not want to replace the first student before we chose the second student. So now instead of it being out of 28, there's one less than that. So now it's out of 27. And if the first student that we chose is in fact left-handed, that leaves us with not 4 students that are left-handed, but with 3 students that are left-handed. So my chances of choosing the second student who is also left-handed would be 3 out of 27, which comes out to be, when I multiply that, roughly about 0.016. So what we would say there is there's about a 1.6% chance of choosing two students where they're both left-handed. So in terms of a general multiplication rule for when we're talking about two events that occur in succession, so this right here is what's called the general multiplication rule. So remember that this part of the probability, that's the probability of A and B both occurring. So what we would say there is that the probability of A and B is equal to the probability of A times the probability of B, given that A has already occurred. So typically we use this multiplication rule. This multiplication rule works for everything, but we typically use this multiplication rule for events that are not independent. So I might want to make a note of that there. So there's a different multiplication rule that we use for events that are independent, but this general multiplication rule works regardless of whether events are independent or not, but this is typically what we use for events that are not independent. So as far as an example goes for something like this, the question here says, the Pew Internet and American Life Project finds that 93% of teenagers, we're classifying them as 12 to 17 years of age, use the internet, and that 55% of online teens have posted a profile on a social networking site. And the question says, what percent of teens are online and have posted a profile? So one of the things that we're going to do with this here, just in terms of organization, is to make a tree diagram. So what we're going to start here is with the first part, which is the 93%. So what we have here is 93% of teens online. So if 93% are online, that means that 7% are not. So we have that there. And then of that group, we have 55% say that they've posted a profile to a social networking site. So for those that are online, let me sort of clean this up here. So for those that are online, and that's this strand right here. So we have 55% of those have posted a profile to a social networking site. So that means that 45% have not. So that's this end of the table here. And then for those teens that are not online, there's a 0% chance that they've posted a profile to a social networking site, because if they're not online, they have not posted a profile. And then the probability that they haven't posted a profile is 1, because if they're not online, then they're not posting a profile. So to find what percent of teens are online and have posted a profile, essentially what we're looking at is this group right here. It's the group that is online and has posted a profile to a social networking site. So in terms of probabilities here, here's the probability that a student is online. Here's the probability that they've posted a profile to a social networking site given that they're online. So in terms of finding the probability for those, essentially we're going to take these two and multiply them together. And when we do that, we get roughly about 0.5115, which in this case means that roughly about 51.15% of teens are online and have posted a profile to a social networking site. So some other sort of examples that kind of go with this, I think this is a pretty good one here. So you have video sharing sites led by YouTube are popular destinations on the internet. Let's look only at adult internet users aged 18 and over. So what we have here is about 27% of adult internet users 18 to 29, another 45% are 30 to 49 years of age. Let me just kind of mark these here. So I got this here. And then the remaining 28% are 50 or over. So that's this group here. The Pew Internet and American Life Project finds that 70% of internet users aged 18 to 29 have visited a video sharing site. So that's this group here. 51% of those aged 30 to 49 have, and then finally 26% are 50 or older. And the question says, do most internet users visit YouTube and similar sites? So to answer this question, what we're going to do is we're going to create a tree diagram here. So just kind of giving you sort of a synopsis of what we did here. So first we kind of broke it down by internet users. So we have 27% are from 18 to 29, 45% are from 30 to 49, and then 28% are 50 and over. And then out of each of the different groups, have they posted videos to a video sharing site? So in the 18 to 29 age group, 70% have, which means 30% have not. And then in the 30 to 49 group, 51% have, which means 49% have not. And then in the 50 and over group, 26% have, which means that 74% have not. And then these probabilities here come from simply just multiplying. So for instance, this probability here I get from multiplying 0.27 times 0.07. This probability here I get from doing 0.27 times 0.03. So that gives me the probabilities for all these different events here. I sort of noted what they were. So the question says, what percent of all adult internet users visit video sharing sites? So what we're talking about here is all the yes groups. So that's this group here, that's this group here, and that's this group here, and that's what these basically correspond to. And what I'm going to do with each of those probabilities is I'm going to add those together, which comes out to be roughly about 0.4913. So roughly about 49.13% of adult internet users visit video sharing sites. So that's just another tree diagram use with some different things involving conditional probabilities and that general multiplication rule. So what we're going to finish up with is this right here. And the question says, a computer company makes desktop and laptop computers at factories in 3 states, California, Texas, and New York. The California factory produces 40% of the company's computers, the Texas factory makes 25%, and the remaining 35% are manufactured in New York. Of the computers made in California, 75% are laptops. Of those made in Texas and New York, 70% and 50% respectively are laptops. All computers are first shipped to a distribution center in Missouri before being sent out to stores. Suppose we select a computer at random from the distribution center. So, give you a few minutes. Try these two questions on your own. So for number one, if we're talking about constructing a tree diagram, I got this here. So I'm going to start with the states. So I have California, I have Texas, and New York. So the probability that a computer is made in California is 0.4, so I'm going to put that here. The probability that a computer is made in Texas is 0.25, so that's going to go here. And then the probability that a computer is made in New York is 0.35, so that's going to go here. So in terms of the types of computers, we have laptops and desktops. So the probability that a laptop was made in California, and I'm just going to abbreviate laptop with, we should do that with LT, that's going to be 0.75 here, which means that the probability that a desktop was made in California is 0.25. Then for Texas, the probability that a laptop was made in Texas is 0.7, which means the probability that a desktop was made in Texas is 0.3. And then for New York, the probability that a laptop was made in New York is 0.5, which means the probability that a desktop was made in New York is also 0.5. So in terms of what I have here, so probability-wise, the probability that a computer was made in California and is a laptop, if I do 0.4 times 0.75, this comes out to be roughly about 0.3. And then the probability that a computer was made in California and is a desktop, I can find that by doing 0.4 times 0.25, which is 0.1. And I'm going to do each of that for all the different computers that are made in the other two states. So this would be 0.175, as with this as well. This would be 0.075. And then these two down here, these would both be 0.175. So that's what number one would look like. Number two, the question says, find the probability that a computer is a laptop. So remember that a computer could be a laptop that's made in California, or it's made in Texas, or it's made in New York. So here is the notation for the laptop made in California. Here's the notation for the laptop that's made in Texas. Here's the notation for the laptop that's made in New York. So from our tree diagrams, we're basically looking at these probabilities here. 0.03, 0.175, and 0.175 again. And if we add those together, this would come out to be roughly 0.65. So that's just some different things that we're talking about in terms of tree diagrams, some different things with conditional probabilities, as well as some different things involving the general multiplication rule. One of the things that we're going to look at next is a multiplication rule that's involved for independent events, which is a little bit easier to work with than the general multiplication rule, as well as some different things involving multiplication rules with events that are what are called mutually exclusive.